Today, we want to look at some finding antiderivatives, and we want to distinguish between finding a general antiderivative and finding an antiderivative and then using an initial condition to figure out a value for the plus c. All right, let's take a look at these let's find a couple of general antiderivatives. So a general antiderivative means we're going to have the plus c. If we have an initial condition, then we're going to figure out what the plus c is equal to. Let's start with the general antiderivative. We have a few examples here. So if f of x is x squared plus 2x, then here we have terms. So we're just going to add one of the exponent and divide by the new exponent. So I'll call the general antiderivative, let's say it's the capital f of x. We'll add one to the exponent and divide by the new exponent. If I read the square root of x as an x to the 1/2 power, we add one to the exponent and divide by the new exponent. And then we put plus c, because the general antiderivative will always have our constant of integration. For sine of 2x, we're thinking what function has a derivative of sine of 2x? And so that means we're going to have a negative cosine of 2x, but we'll have to divide by the coefficient of x. So our antiderivative will be negative cosine of 2x, and then we'll have to divide by the derivative of the inside since it's constant. And then we put plus c because we're finding a general antiderivative. If we wanted to check, if we take the derivative of negative 1/2 cosine of 2x plus c, we get negative 1/2 times the derivative of cosine of something is negative sine of something times the derivative of the something. So the negatives cancel out, and the 1/2 will cancel out with the 2 that we get from the chain rule. The derivative of the plus c is 0, so we got the right function. Now let's look at this second example. It looks like it has the same thing. Find capital F such that capital F prime is x squared plus square root of x. That is, find the general antiderivative. But then we have this additional piece of information. F of 0 is equal to 4. And that's a piece of information about the function that will let us figure out what the plus c is. So we use the function to find the general antiderivative. And the f of 0 is equal to 4. This is an initial condition. And we're going to use this to find out plus c. So first, we find the general antiderivative. So capital F at x will have the form 1/3 x cubed plus 2/3 x to the 3/2 plus c. So that's we get the general antiderivative, knowing that f prime is x squared plus square root of x. Now, since f of 0 is equal to 4, I can plug that into my function and figure out what c is equal to. So if I plug in 0, we have f of 0. This is going to be 1/3 times 0 cubed plus 2/3 times 0 to the 3/2 plus c. So f of 0 is equal to c which is supposed to equal 4. And so that tells us that c is equal to 4. So the function that we were looking for that fits both parts of this description is f of x is 1/3 x cubed plus 2/3 x to the 3/2 plus 4. This is a function that fits the description. Notice we have a specific value for c, not just some generic arbitrary constant of integration. The initial condition allowed us to figure out what the constant of integration was. So we can do this with our sine of x function too. So let's suppose that we want to find a capital G of x such that capital G prime of x is equal to sine of 2x, and capital G of 0 is equal to 4. Same structure that we had before. We have the derivative of a function, so we'll find the antiderivative, the general antiderivative. We'll plug in our initial condition to find the constant of integration. So general antiderivative, the capital G of x will have the form -1/2 cosine of 2x plus c. Since G of 0 is equal to 4, if we plug in 0, we get -1/2 times the cosine of 2 times 0 plus c. Cosine of 0 is equal to 1, so we get -1/2 plus c is equal to 4. And so that tells us that c is equal to 4.5. So now we know what specific function we were looking for. The function g of x that fits both these descriptions, both parts of the description, is going to be a -1/2 cosine of 2x plus 4.5. So that function capital G fits the description that g prime is equal to sine of 2x and g of 0 is equal to 4. What we want to note is that the general antiderivative is going to look like a family of functions that are all just vertically shifted. They're all the same. The only difference is the vertical shift, the constant at the end. So here is where the general antiderivative, where we, given the derivative, we use the general antiderivative is a family of functions. The general antiderivative is a family of functions that all have a particular form. The only thing that's changing is the constant term. So if, for example, we could find another g of x where g prime of x is still sine of 2x, but this time g of 0 is equal to -3. So we're going to have the same general antiderivative. So this g will be in the same family of functions, but we'll have a different constant term. So the same, this is going to be, this tells us we're going to be using the same family of functions, but we'll get a different constant term. Our family of functions is still g of x negative 1/2 times the cosine of 2x plus c. And since g of 0 is equal to -3, negative 1/2 times the cosine of 2 times 0 plus c is equal to -3. So that tells us that negative 1/2 plus c is equal to -3. So c is equal to -2.5. So the function we're looking for in this example is in the same family as the previous example, negative 1/2 times the cosine of 2x plus some constant, but in this case, the constant is -2.5. Any questions? One thing to keep in mind is that when we're finding a definite integral, when we're calculating a definite integral, the fundamental theorem of calculus says the capital F is an antiderivative. So recall the fundamental theorem of calculus says that the integral from a to b of f of x dx is capital F at b minus capital F at a, where capital F is an antiderivative of little f. The reason it says an antiderivative is that the fundamental theorem of calculus works with any of the antiderivatives. They're only off by some plus c, and if f of b has a constant and f at a has the same constant, they'll cancel out. So notice that the constants of integration will cancel out. So the constants of integration will cancel out of the f of b minus f of a. For example, if we have the integral from 0 to pi over 4 of sine of 2x dx, we need to find an antiderivative of sine of 2x, which we may remember from our previous example because lazy teacher is lazy. So we find the antiderivative, which will be minus 1/2 cosine of 2x. If we have the plus c, it's not going to make a difference. We evaluate this from 0 to pi over 4. So I have a negative 1/2 times the cosine of 2 times pi over 4 plus c minus a negative 1/2 times the cosine of 2 times 0 plus c. So we can see in this scenario that we have a c from the capital F at b minus a c from the capital F at a. The c's cancel out. So it doesn't matter which antiderivative we use when we're calculating a definite integral, because we're doing capital F at B minus capital F at A. Whatever constant was there will just get canceled out. So we have minus 1/2 times a cosine of pi over 2. Minus and minus makes plus 1/2 times the cosine of 0. Cosine of pi over 2, 0, 1, 0 is 0. And cosine of 0 is 1. Any questions? Want to use this antiderivative business and some area problems. So let's take a look at this example. So here we want to find some area. So finding area, this calculus class. So finding area means we're going to be doing some definite integrals. Exact values of this area means that we're going to have to use our fundamental theorem of calculus. It's going to work out to a rational number anyway, because I picked some nice polynomials for us, but that's the way that we should think about what's going on. Area, this part makes us think definite integrals. And since I invoke the exact value, the exact area, that makes us think we're going to have to use the fundamental theorem of calculus rather than just approximating it with our approximation machine. So let's take a look at what this region looks like. I just said the region between x squared and 2 minus x squared. So let's take a look on our graphing calculator. So we've got the area under one parabola and above another parabola. So we got these two parabolas, and we want to find that little kind of squished football shape area between the 2 points of intersection. So let's see what we need to do to find this. Let's first draw a picture of what's going on here. I've got one parabola, the x squared, is going to be the parabola going up. And I got this downward facing parabola, which looks like I made it, that one turned out in blue. So the first thing we'll notice is that since these are just both polynomials, their antiderivatives are going to be polynomials. And when we plug in our integers, wherever these intersections are, we're going to get a rational number. All right. So we're looking for this area in between these two curves. We know we're going to be calculating some definite integrals. So we're going to need to know the interval over which we are integrating. First, let's find the interval over which we integrate, because we need to find out where these points happen, even though now that we've drawn it carefully, we know that this happens at -1 and 1. So we can find the points of intersection by putting the two equations equal to each other. We're trying to find out where these y coordinates are the same. So let's find the points of intersection. By taking x squared and setting that equal to 2 minus x squared. That is y equals y. So I need to solve for x. I've only got, x appears more than once, but if I gather my x's, I can write this as 2x squared is equal to 2. Divide out the 2, x squared is equal to 1. And this gives us our 2 points of intersection. X equals plus or minus 1, just like we suspected. We start with something where we know what the result is, and we see if our method will produce that result. That's how we verify our method. What I need to find is the area under the 2 minus x squared, and I'm going to subtract the area under x squared. So the way we're going to set up the problem is we're going to take the area under the 2 minus x squared, and we're going to subtract the area under x squared. And that'll give us the area between. We'll take the area under 2 minus x squared and subtract the area under x squared. The area under 2 minus x squared will be the definite integral from -1 to 1 of 2 minus x squared dx. And we'll subtract the area under x squared, which is going to be the definite integral from -1 to 1 of x squared dx. Since both these definite integrals are using the same interval from -1 to 1, so both integrals are on the same interval. Both integrals use the same interval. I can combine them into one definite integral. So I could say this is the definite integral from -1 to 1 of 2 minus x squared minus an x squared dx, which we would want to clean up as the definite integral from -1 to 1 of 2 minus 2x squared dx. Since I said find the exact area, we'll use the fundamental theorem of calculus. So the antiderivative is going to be 2x minus 2/3 x cubed. In both cases, add 1 to the exponent, divide by the new exponents, and we could read 2 as being 2x to the 0 power. Or we could just remember that the integral of a constant is a constant times the variable. Then we'll evaluate from -1 to 1. So we'll have 2 times 1 minus 2/3 times 1 cubed. There's my capital F at B. And we'll subtract 2 times -1 minus 2/3 times -1 cubed. There's the F, capital F at A. So let's see what we got. We got 2 minus 2/3 minus a -2. So it's going to be -2. And negative makes plus 2/3. Right, -2, negative times negative is positive. But we're subtracting. So minus and minus is +2 minus another 2/3. So we got 4 and -4/3. Let's see. So that's 4 minus 1 is, 4 minus 1 and 1/3. 4 minus 1 is 3. 3 minus 1/3. 2 and 2/3. You wouldn't want to write all this down. This is all just whatever nonsense takes place in my brain to make me be able to subtract 4 minus 4/3. Any questions? Earlier, I mentioned that this is actually a value that our calculator can handle. So if I just math 9 to bring up numeric integration and integrate the function 2 minus 2x squared with respect to x from -1 to 1 and have it convert to a fraction, then we get the 8/3. So it all worked out. In the beginning of the problem, we were primed to use the fundamental theorem of calculus, specifically because we were at the exact value, the exact value was called for. Area said we're going to be doing a definite integral. Exact value said we're going to be using the fundamental theorem of calculus. In this case, we could have gotten at the fundamental theorem, or the exact value without the fundamental theorem of calculus with a machine, but that would only cover us in this case. If I trade my functions for some transcendental functions, then all of a sudden we're going to have to use the fundamental theorem of calculus, and the machine will not be able to give us the exact value. I guess I could have gone with some square roots of non-perfect squares too. That'll work. Any questions? All right. This is our, that's all we wanted to do today. Just wanted to remind ourselves of how the fundamental theorem of calculus works. We want to reconnect, make sure that this antiderivative and integration stuff is connected and that it connects back to our ideas of area. And we also want to reinforce the notion that this antiderivative business is the derivative process in reverse. It's the inverse of the derivative, almost. And for details, the almost is specifically because of the plus c. The derivative of all constants is 0. So when we integrate 0, we don't know what constant to go back to unless we have another piece of information. Any questions? Comments? Snide remarks? From a doing work in this class standpoint, all the homework assignments that I'm going to assign are available. So you can finish off the homework portion of this class now. You wouldn't, I don't know, if you haven't started on like the chapter 5 stuff, then you're probably not going to finish today. But it's conceivable that you could be done with the homework portion of the class. Then I just have to upload some quiz portion of the class, and that's going to serve as our final exam. So we're not going to have a final exam where we all have to meet in the same room at the same time. This way you can take the final exam when you feel like doing it, and it's going to be broken into parts. Because otherwise it's really hard. I find students really don't like it when there's like a 10 question thing. They tend to want to sit down and do all 10, when I would rather have you do just one. Like if you can hammer out all the parts in one sitting, then that's great. But if you're going to take more time to do the problems, I would rather break it into pieces for you so that you can do one piece and say, okay, I'm done with that piece. Does that make sense? That's the structure that we want to use. All right, so keep in mind for another module showing up on Canvas, which is going to be some quiz problems. You will have, as usual with quizzes, you will have unlimited, just like the homework, you'll have unlimited attempts on all the quizzes. So you keep going until you get things right. Some of the quizzes will be automatically graded. I can set them up to be automatically graded. And some of the quizzes I'm going to have to grade myself. So I have to grade them by hand. So you'll have to wait until I do the grading before you do your corrections. But you'll all have opportunities to do corrections on all of your work. All right, that's going to do it for today. Hang on, I got to shore this up before these thoughts leak out. There we go. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.